Hey, my wonderful little students. Today we're going to talk about oxidation numbers and how they actually relate to the different families that we looked at when we discussed the periodic table last set of notes, and how they're different from valence electrons. So looking at the oxidation numbers, we kind of got to the idea that all atoms and all elements want to be happy. And what really makes it happy is by having a stable outer energy level. Okay, so when we talk about the outer energy level, we're really talking about our valence electrons. Okay, so all atoms want to get a stable outer valence electron shell, or a stable outer energy level. And the way that that happens is that atoms are going to gain or lose electrons to become more stable. Realistically, what they want is they want to have 8 valence electrons on their outer energy level, because 8 electrons means they have a full octet. Now, whether that means you happen to be sodium at Na and you happen to have one shell, 1, 2, 3, 4, 5, 6, 7, 8, 2 shells, or that third shell with a 1, or we look at the other side for our Cl, and I should have drawn these out earlier. 1, 2, 3, 4, 5, 6, 7, 8. And our final one, 1, 2, 3, 4, 5, 6, 7. Okay? Notice how this chlorine has 7 valence electrons. And notice how this sodium over here has 1 valence electron. Well, basically what we're trying to get at here, they want to have 8 valence electrons. Now, for this one, for the chlorine, it makes sense that gaining 1 to go from 7 to 8 just makes sense. For the sodium, for instance, when you lose this 1 to go from 1 to 0, if you get rid of that, the inner shell has 8 valence electrons. So it doesn't matter if you're gaining or losing, your goal is to get to 8 valence electrons. And we're going to continue, or I'm going to continue saying, you're trying to get to 8 or 0. Okay, and 0 really means that the shell below it is full at 8. Okay, we kind of hit on the octet rule, but basically the octet rule is that atoms are going to form bonds with other atoms in order to have 8 valence electrons. Okay, having 8 valence electrons is basically what we're going to concentrate on for the coming weeks in this class. Now, there's multiple ways we can go through this. Atoms can share electrons, or they can transfer electrons through to different elements. Okay, and that's going to be where we talk about the next PowerPoint. Right? And elements are not just going to gain or lose electrons. It's not like we just magically pull an electron out of space. Okay, you need to have another element. So this is key. There needs to be another element that you are taking electrons from, or that you are giving electrons to. It's not like there's just this magical bin that you are putting electrons in or taking electrons from. There needs to be either a pairing or a grouping of 3, 4, 6, whatever, but there needs to be other elements involved for those electrons to actually get transferred or shared. Okay, so that's what our octet rule is discussing. Anyways, the way that we figure out exactly what's going to get shared and how that's going to happen is by using oxidation numbers. Oxidation numbers basically just tell us how many electrons, are going to be gained or lost when we bond, and that ranges from -4 to 4. Now, let's think about this for a sec. Why would we range from only -4 to 4? Well, it's because if you're trying to get from 0 or get to 0 or get to 8, there's no way that I can be further away than 4 numbers from 8 or from 0 without going in the opposite direction. So for instance, if I go through and say this 1, 2, 3, 4, 5, 6, 7, and this guy's 4, if I happen to say, hey, I have 2 valence electrons, well, I'm going to travel 2 to the left to get to 0, so I'm going to give away 2. If I happen to say I have 6 valence electrons, I'm going to gain 2 more to get to 8. At no point are you going to gain or lose more than 4. So we've got a range from 0 to 4. All right. And how are we going to go through and figure out how many oxidation numbers each one has? Well, we can go through and we're going to teach you the system first, but after we get through this slide, we're going to show that every family actually has its own set of valence electrons. Oxidation numbers. All right. So first we got to figure out how many valence electrons a neutral atom has. So if we're going to use an example, let's say nitrogen. So nitrogen Nitrogen happens to be isotope notation. We're talking a 14 and a 7. It's neutral. So how many valence electrons does a neutral atom of nitrogen have? Well, it happens to have 5. So we've got 5 valence electrons. Okay, so we know that we've got 5 valence electrons. Is it going to go up to 8, or is it going to go down to 0? Which is easier to get to? Well, being at 5, it's easier to go up to 8, so we are going to gain electrons. Now, how many are we going to gain? We're going to go through and gain 3. Okay, and then we got to count how many we're going to gain or lose. So we talked about the fact that we're going to gain 3. If we're gaining, the charge is going to be negative. So nitrogen happens to have an oxidation number of negative 3. Okay? If we were going to lose electrons, so like let's say we happen to have the element of magnesium, Mg, which has 2 valence electrons, it's easier to drop down to 0. And because we're losing electrons, we're going to be at plus. So you're actually going to have an oxidation number of plus 2 if we're talking about magnesium. All right? So we can go through and you can figure out each individual atom and each individual element like that. But an easier way is just going through and memorizing the periodic table, because the periodic table actually has all the oxidation numbers on it. We know that your alkali metals happen to want to lose 1 electron, and that puts them at plus 1. The alkali earth metals want to go through and... Okay, that apparently didn't get happy. Come on, stop. Your alkali earth metals want to go through and lose 2. Your transition metals, and again those are weird because they have variable valence electrons, they're going to have a variable oxidation number, and we'll always give you an oxidation number for that. Your boron family is always going to want to lose 3, while your nitrogen family is going to always want to gain 3, so it's going to be minus 3. Oxygen family is always going to be minus 2 because it wants to gain 2. Your halogens are always going to be minus 1 because they want to gain 1. And here's where we get to the 2 weird ones. Okay, your noble gases, they don't want to do anything. They're already happy. They're already content. They already have full valence shells. So they're going to stay exactly where they are. So they don't gain or lose any. So they've got an oxidation number of 0. Carbon, on the other hand, we go through and we call carbon plus or minus because it could go either way depending on what it's bonding to. Okay? If it's bonding with something over here, it's going to give up electrons. If it's bonding with something over here, it's going to take their electrons. It basically does whatever makes the other atom happy. Okay? So if you wanted to roll through some of the practice ones, you could. I would take a second, I would pause, and I would try out these. Okay? So again, if we've got lithium, we know that our valence electrons, valence electrons happen to be 1. So if we got 1, we're going to lose that 1, and losing that 1 means that we happen to be at a plus 1 oxidation number. Work your way through the other 6, and we'll go ahead and pop some answers up there in a second. Seriously, give it a pause. Work them out. Anyways, here are complete answer sets for each of these. We know our sulfur, because our sulfur happens to have a valence electrons of 6, it wants to gain 2, and gaining 2 is going to put it at negative 2. All the way down to neon, which is a noble gas and does not want to go through and interact in any way. So these are oxidation numbers. Seems like a fairly simple concept, but these are going to be massively important when we talk about bonding in the next unit. We're actually going to break that presentation down into 2 different videos because of how complicated it can get. Anyways, have a wonderful day, children. We'll do it again later.